This is a slide I've been using for about a decade now, so I'm grateful to Ben and Adam and Allison and the rest of our Foresight hosts for having me, because this book in particular has influenced my work tremendously. And what I'll be showing you is the results of about 10 years of research in the direction of building printers. And when I read this book, Engines of Creation, there's one particular quote that stood out to me. And it's that the future's tools exist now only as ideas and possibilities implicit in natural law. And I believe that there is no physical fundamental reason why we can't build at these levels that we've been discussing today. We just haven't determined yet how. And what I'll be talking about is building organic systems with the highest level precision we can. And we already have a method to build atom by atom at the sub-nanometer scale, and it's called organic chemistry. The problem is, in the context of building in multiple dimensions, that of the 100,000 or so reactions that organic chemists have, only about 5 or so have ever been used on the surface. And there's several reasons for that. One is that the people that are familiar with instrumentation are not familiar with the chemistry. They're two completely different languages. And as a result, the tools for doing organic chemistry on surfaces have not evolved to allow us to build multidimensional structures. So the bottleneck that my group has been addressing is this one. How do we increase our capacity to do organic chemistry on surfaces with control over where you are creating the bonds? To do this, we built a machine that we call the hypersurface printer. And it's outlined here. What this involves is a microfluidic system. So that's the multicolored syringes, and they flow different reaction mixtures into a fluid chamber. The challenge for building multiple dimensions using organic chemistry can be solved if you choose reactions that do not go spontaneously. What we're doing here is to build up complexity. We use reactions that only are driven when the particular space is illuminated. That way, what you can do is you can control organic chemistry spatio-temporally. What that means is you flow in one liquid, you hit the surface with light, the reaction only occurs where light hits the surface, then you can change that out and flow in another system. The way we control delivery of light in this iteration is with a digital micromirror device that can just be controlled by a computer. And the final element to this is you have to correctly choose the chemistry. There's 100,000 or so reactions to choose from. The limitation in this particular context is the reactions must be photo-driven. I've shown one reaction in the top right corner. This is just atom transfer radical polymerization, which is one example of a photo-driven reaction where the height of the polymer is just controlled by the irradiation time, and we can control that with sub-nanometer resolution, simply by controlling the irradiation time and the reaction conditions. So the question is, once you have one of these tools, what can you build? And I'll show you just one example from my group that considers building in multiple dimensions. And to think about the structures you can build, you need more than 3 dimensions, like the Rubik's Cube that people have been putting. I think of that as a 4-dimensional material, where you have the 3 spatial dimensions, and then any voxel within that structure must also be defined by its chemical composition. So let's look at some multidimensional structures. I'll just show one. We call this the 6-dimensional hypersurface, where what we've done is we've embedded 2 orthogonal hidden images within the same area. And the design and the fabrication process is shown here. What we're using is these grafted from surface polymerizations. So what we're doing is we're growing from the surface and changing or swapping in inks and coordinating the light with the ink delivery. So we have two different types of responsive inks in this system. The first is called polynipam. This is a molecule that shrinks when you heat it up in aqueous systems. And then we have a fluorescent dye that we embed. And so the first thing that we did here was we built a hexagon out of nipam. Then we backfilled to the top of the hexagon with an inert polymer. On top of that, then we continued growing our inert polymer with a vacancy for a fluorescent polymer in the shape of a tetrahedron. So the overall three-dimensional design, or four-dimensional design, or six, depending on how you count your dimensions, is shown on the left. Optically, this just looks like a flat surface, but when you hit it with fluorescent light, the tetrahedron emerges, and if you hit it with, if you heat it up, then the benzene ring appears. So this is just one shape that you can draw, or one pattern you can create, but the uses and implementations of these tools are limited only by the imagination of the user. That's all I have. Thank you again to our hosts, and thank you for your attention.
Questions?
What kind of speeds are you getting with your current process?
A pattern like the one shown here takes about 15 minutes.
Yes. The scale of the features here?
Here, the square that outlines the tetrahedron is, I believe, about 20 microns.
Yeah, that was also part of my question. I was wondering about the precision of the DMD you're using. Like, what's the smallest pixel size you have tried to pattern these NAPAM gels?
That's a good question. With the DMD, the simple iteration I showed here, our pixel resolution in X and Y is 2 microns, and in Z, that's dictated by the chemistry and can be sub-nanometer. We have other iterations where we can get feature sizes down to about 50 nanometers.
How is this different from conventional 3D printing with light?
Okay. There's a few different parameters you want to look at. Feature size, and then chemistry that you can do. And I guess those are the only two metrics that really matter. So it differs in feature size and the chemical composition, and I guess probably the dimensions of the structures you can form, but that's just the same thing as the other one. So yeah, chemical composition, feature dimensions.
Just with regard to the very small number, just with regard to the very small number of surface reactions, in terms of catalysts, it's all catalytic chemistry is effectively surface driven. Does that include catalytically driven?
Okay, that's a very good point. Lots of our catalysts are done on surfaces. What I meant,
It's a surface reaction, right?
yes, what I meant is for building architectures from surfaces. That's a very good distinction.
Wonderful. Thank you.
Thank you.